Hey, everybody, welcome to the next episode of the Stocks and Crypto SQL Show. My name is Attila Toth. I'm a developer advocate at Timescale. And as I mentioned, this is episode number 5 for the Stocks and Crypto SQL Show, which, if you haven't watched the previous live sessions, they are available on YouTube. All of the recordings are on YouTube. We are live on Twitch and YouTube as well. And basically, this show is about the different ways you can use TimescaleDB uh, with crypto data and stocks data. And we are trying to help the community to um, improve their query performance or show tips and tricks how to store data, this kind of data, efficiently with TimescaleDB. And today's episode is actually, let me share my screen. Today's episode is about downsampling and how you can use TimescaleDB to downsample your data, which can improve query performance and reduce storage costs, which is really useful if you have a lot of historical data. And if we talk about, for example, stocks or crypto prices, if you store this kind of financial data, you are probably going to have some of these problems that I'm going to talk about, and I will show you how TimescaleDB and how downsampling can help with those problems. I'm watching the chat as well, so if anybody's watching it and you guys have questions, I will also be able to answer, hopefully. All right, so very quick agenda. It's not going to be a very long stream. So first, we are going to talk about just generally what is downsampling and why it can be useful for you. Then I'm going to show you how you can downsample with TimescaleDB, and then finally show you some next steps in case you want to continue learning more about TimescaleDB and continue your learning journey. Okay, so what is downsampling and why is it useful? So first of all, downsampling means rolling up very granular data into less granular or less detailed data. Now, what does it really mean? So to understand what that means, maybe first let's look at some problems that downsampling can help you solve. So one of these problems is that you might have too much data, and having too much data can make your queries slower, and it can also increase your storage costs. And obviously, these two things are bad, especially if if you have time series data and you want to analyze the historical data, because it's quite easy to collect a lot of historical data when you have time series, or when you have a time series workload. Maybe you have a sensor that is recording data every second, or even every minute. In the case of stocks, for example, where it's fairly normal to record stock prices every minute for a lot of different symbols, and over time uh, it adds up, and it's just a lot of data to store. And one thing to notice is when you have a lot of data, obviously the bigger part of your data will be historical data. It will be older data, so not from the past hour or the past day. It's going to be from last month or last year, or even older data. And one thing which you might find in your own use case while you are using TimescaleDB and you have time series data, is that as the time series data gets older, it might get less valuable on a record level. And the record level means that individual rows. So for example, in the case of stocks data, let's say you are collecting data every minute. So for every minute, you have one row um, getting ingested, uh, and and over time, you might not care about that one specific row, but you care about it right now. So, for example, it might be more interesting for me to know what's the I don't know, price of Apple, the Apple stock, in the past hour, or what was the opening price today. So that could be more important than to know, let's say, what was the price of Apple stock, I don't know, 2020 November 12, 6:15 in the afternoon. So that might be less important to know, but it might be still interesting to know what was the opening price on that day in 2020, or what was the opening price in that month, and the closing price in that month. So you get a sense of the trend, and you get a high level view of all their data. But the closer the data to now, it's probably more valuable. And another problem is that maybe you ask why, or maybe it's it can be a solution in some cases, but you might ask, why don't you just delete data that you don't really need anymore? But the problem with this kind of aggressive data retention policy is that with this, because you are literally deleting data from the disk, you won't be able to reach it anymore, and so you lose practically all the value from your historical data, because you won't have historical data. And and that can be a problem, because this way you don't even get those kind of insights that you can get from downsampling, like the ones I mentioned, the high level trends, and basically just understanding what is considered normal in your data, or at least what was considered normal in the past. So those are the kind of things you can get from downsample data, but you won't be able to get these if you just remove data altogether. And I think those are all the problems. So now let's look at some of those things that downsampling can help you with. So basically, downsampling eliminates the need to store records that you don't need anymore. Again, going back to that Apple stock example, you probably don't care what was the price, the exact price, what was the price in the exact minute of 2:15 p.m. in the afternoon in November 2019 or whatever. So you don't need that one specific data. On the other hand, you do need that kind of data from today. Like if you are into stock trading, or if you are watching crypto prices, or whatever data set you have, you want to know what was the price an hour ago or 2 hours ago, because it's much more relevant for you. But with downsampling, you don't need to store those very old historical records that you don't really use anymore. You don't really need that kind of information anymore. Now, the other aspect of downsampling data is that instead of deleting data, what downsampling does is just basically stores the aggregated version of the data. So, and it does it using any kind of function you want to use, like sum, average, min, max, or the first and last hyper functions, for example. So these aggregation functions can help you still be able to store the high level values, so you can get the high level trends and the high level overview of your historical data. And instead of storing data for every minute, you store data for, let's say, every day, or just every week, depending on how much you want to downsample. And this is connected to the other two benefits. Basically, downsampling helps you get rid of unused records, but still be able to analyze. You can still be able to. You will be still be able to analyze historical data, because you will be able to see at least the trends. You will be able to see the trend line. You will be able to get a sense what does normal look like in your data set, and that can be really, really valuable. All right, now let's look at some examples what downsampling looks like. First, on the front end. So if we talk about a chart, for example, so this chart here, this is just a line chart, a time series chart for a stock symbol, and it shows the stock price of that symbol. I think it was actually Apple from between July and August, but it basically shows the values over time for Apple, the stock prices over time. And as you can see, there are a lot of data points on this chart. But actually, if you look at this wide range, you don't really get to see what those low level or record level values are. Basically, this chart can help you see the trend line. And and this is before downsampling. Now let's look at what it looks like after downsampling. So as you can see, this basically so these are the same. These charts show the same date range, but after downsampling, you have much less data points. And but you can still be able to see the trend line. So basically, if you don't care about the specific details of your data, downsampling can help you still get this high level data, this high level overview, and but at the same time you store less data on your disk, and so you save on storage costs probably, and your long range queries will be probably faster. And I will also have some queries later on, so I will actually show you how it works. So there's a question: is it sort of like taking snapshots of data before deleting? Yes, I think it's a good way to say this. And basically, time series data, like all kinds of time series data, is just taking snapshots. But you can take snapshots like very often, like every minute, every second, and that will result in a very granular data set. And this is what downsampling helps with. It makes your data set less granular, so you will have basically less snapshots actually stored on the disk, and basically that provides those two benefits that I mentioned: the reduction of disk storage needed, and probably faster long range historical queries. But yeah, good question. Right. So another example, we can look at the raw data, like what is behind those two charts that I showed you. So before downsampling, this is a data set that you might have if you are storing stocks data. This is the intraday stock data for Apple from the month of September, 22nd of September this year. As you can see, we have the typical open, high, low, close volume kind of data set. And what you can also notice is that we have minute level data. So we have one record for each minute for Apple. And this is, in this context, this is considered a very granular data set. Obviously, it could be more granular, but this is the kind of sample data that I used for the chart that I showed before. Now let's see what happens if you downsample this. Um, what happens is that instead of having one row for each minute during the day, you have one row for each day. And so again, this is the same kind of data, just after downsampling. So if you look at the time column, which is called bucket after downsampling it, instead of having one row per minute, you have one row per day. And this way you have much less data to store. You have much less data to query if you are trying to query data from a longer range historical data. And so this is what downsampling will look like after you have downsampled your data. Downsampling is downsizing your samples. Yeah, basically, yes. All right, so now let's jump over to 𝗥𝗲𝗹𝗲𝘃. Well, I actually have a slide before that, so let's do that first. But I'm going to show how to actually do it in TimescaleDB. But first, let's discuss the process. So you could manually downsample your data. This is a one-time job. You just do it one time, and I will show you how to do that. But you can also, I will also describe how to automate this whole process. So you downsample your data that you consider older automatically as you have new data coming into your database. But first, let's look at the manual process. So first, you need to create a downsampled materials view. In TimescaleDB, the most efficient way to do this is by using continuous aggregates, which is basically a materialized view for time series data. And it's one of the flagship features of TimescaleDB. We have a lot of content on our YouTube channel about continuous aggregates if you want to learn more. So the first step is to create a continuous aggregate. And the second step is to actually delete the older data. And with TimescaleDB, you can use the drop chunk function, which is going to efficiently remove historical data or any data that you want to delete. And you can we will have links in the description for both continuous aggregates and drop chunks and other functions. But basically, the drop chunk function doesn't remove individual records, because that would be really slow. It removes chunks in TimescaleDB, and this way it's much more faster to delete data. So that is the manual process, how to downsample data. I'm going to show you in action in a minute. The automated downsampling process is very similar. You first create the continuous aggregate, which actually does the job of downsampling as far as using the aggregation functions like min, max, average, and the time bucket function. And then the second step is to set up a continuous aggregate policy. And this will do the actual automation part. And it will contain, well, that's why this is the name of this functionality. But it will continuously aggregate your data. And in this context, it will continuously downsample your data as it comes in, based on the time window that you specify. So, for example, it will continuously downsample data that is older than 1 month, because as an example, in your use case, data that is older than 1 month might be considered historical data, or you don't need that kind of data anymore, so you can downsample it. And the other part of the automation will be a data retention policy. And the data retention policy will take care of actually removing the data. And also, it's very important that these two policies don't conflict with each other. And so the note I have here, the interval being deleted should not overlap with the offsets for the continuous aggregate. So basically, what that means is that data that is currently being added into the continuous aggregate should not be deleted at the same time by the data retention policy, because that could obviously cause some problems. So make sure that your data retention policy doesn't overlap with the time window that you specify for the continuous aggregates policy. And I will show you how you can do that. I think right now, yes. So I will jump over to 𝗥𝗵𝗱 and demo some of these things that I just showed you. Let me increase the font size so you can see it more clearly. All right, so as I said, we are going to work with a stock data set, and which has data from I think from the past year, maybe even more. We will run some query to learn more about the data set in a second. But basically, this is the table definition. This is the typical open, high, low, close, volume kind of schema that you might have if you are storing financial data, stock data, or cryptocurrency data. And it's a hyper table, as you can see. So this is what I'm using in this demo. There's another question, sort of a random question. Is Timescale PD/DF friendly, like read write wise? I'm not sure what you mean. I might ask some colleague if they know what you mean. But if you want to, what do you mean by pandas, right? Yeah, is Timescale pandas data frame friendly? Yes, of course. Reading and writing pandas. Yeah, got it. So yeah, obviously. So in pandas, as I know, there is the read SQL function that you can use to read data from any SQL database. And because TimescaleDB is a Postgres extension, you can use the pandas read SQL function to read data from TimescaleDB into a data frame. If that was your question. And yeah, absolutely. All right, so so exploring this database further, just a little bit, so we understand what we are working with. Let's first see the number of rows in the hyper table. So I'm using the approximate row count function to do that. So if I run this query, see that we have almost 9.5 million records, and these are all stock prices, intraday stock prices recorded on a minute level for different stock symbols. Now let's see what is the time frame of the data set. So the oldest data that we have in the data set is from, let me increase the font size here as well. So in the data set, we have data from 2020 December 21. So that's the oldest data record that we have. And the newest one is from November 12. So it's almost a year of data. Now we will downsample this data set, and I think we will downsample maybe the first or not the first, but downsample all the data that is before September. So starting December 21 last year, we will downsample all the data that we consider historical. And as an example, let's consider historical data, all the data before September. Alrighty, so if we go back to the slides real quick, the first step here, whether you are manually downsampling or you follow the automated downsample process, you need to create the continuous aggregates first. And to do that, you basically need to use the create materials view function, but use the TimescaleDB continuous aggregate, and then define the actual continuous aggregate query that you want to use. Now, in this example, I'm downsampling by 1 day. So basically, instead of having minute level data, I'm going to have day level data. So I'm going to have instead of having 1 row per minute, I'm going to have 1 row per day, and the other usual typical aggregation functions to have the open, high, low, close volume values. So I'm using the first to get the opening price of the day. I'm using last to get the closing price of the day, and then min, max, and sum to get the other values. Now, one important part of this continuous aggregate definition is the with no data. And what this will do is it will not materialize any data right now, which can be useful if you want more control over how you are materializing your data, or what you want to be materialized. And so this is what I'm using right now. If I don't include with no data, everything will be materialized, which in this case I don't want. If I run this query, as you can see, it's instantly done because nothing is getting materialized. But we created the continuous aggregate. Now let's check what is actually materialized, and we are expecting nothing to be materialized. So to see what is actually materialized in the continuous aggregate, you can disable real-time aggregates by setting the TimescaleDB materialized only parameter of the continuous aggregate to true, and this will make sure that after this, all the queries that you use for the continuous aggregate, the continuous aggregate will only use the materialized data. So so that's an important distinction, or that's an important thing to set if you want to only query from the materialized table. So if I disable the real-time aggregates, and then I will try to query some data from the continuous aggregate, then nothing will be returned, which is correct because nothing is materialized. Now, in order to materialize something, we will need to manually refresh the continuous aggregate. Again, this could be done automatically with a data a continuous aggregate policy. But right now we are following the manual process how to downsample data. So I'm going to manually materialize historical data, meaning I will manually materialize data in the continuous aggregate. And as I mentioned, we're going to materialize all the data between 2020, the first data point we have from 2020, and the last day in August. So I'm using the refresh continuous aggregate function to do that. I'm specifying the window start and the window end. So if I run this, this will actually take a couple of seconds, because this is materializing a lot of data. As we seen at the beginning, there are I think 9.5 million records in the database, and most of the data is actually in the time window that we are materializing right now. So that's why this query takes a little bit longer, but it's just a one-time job. You just need to do it once, and then all the queries that you run against the continuous aggregate will be much faster. And after this query is done, we will see what is actually materialized right now. So it's done, and let's see if there is anything materialized right now. Again, just running some query to see if there is anything in the continuous aggregate. And as you can see now, there are actual rows in the continuous aggregate. And again, we disable the real-time aggregate. Um, so the data that you see is materialized, and and even if we have a new data coming in inserted into the database, that will not be shown here unless we materialize it. All right, so now what might be interesting to show is the size difference between the underlying row hypertable and the continuous aggregate, aka the downsampled data set. And with this, you can actually see what kind of reduction you might expect in needed storage space if you use continuous aggregates and delete the data afterwards, which I will also show later. But now let's see the size difference. So to learn what is the size of the continuous aggregate, we let's list all the continuous aggregates that we have currently, because we will need to get the underlying materialized table to do that, by the name of the materialized table. So let's list the continuous aggregates. We just have one, so it's not a huge challenge. But if you had more continuous aggregates in your own database, you might want to filter based on the view name, and that will return only that one specific continuous aggregate that you want to learn more about. So now that we made this query, the information that we're looking for is the materialization hypertable name, because that is the table that actually stores the data. Because conti- under the hood, continuous aggregates is actually based on a hypertable as well, uh, and that's the name of the hypertable. And we are trying to get the size of that hypertable right now. So that's the name. So I'm going to just copy this, and I'm going to paste that here for the hypertable detailed size, which will give us the size of the continuous aggregate. And I'm using PG size pretty to see um, the size in a formatted way. So if I run this, it didn't work because there is no materials hypertable with that name. All right, maybe let's check the name of the. Oh yeah, actually, because it's an internal materials hypertable. So let me go back one step here and including the name after TimescaleDB internal, because this is actually a TimescaleDB internal table where we get this kind of information from. So now if I run this query again, we see that the size of the continuous aggregate is a little bit more than 4,600 kilobytes. So that's the size of the continuous aggregate. All right, let me look at the chat a little bit because I see there are some entries. All right, so we put some links in the comments that you might find useful. How do I set the chunk interval for the materialized table? So if I go back here, I think you are referring to the continuous aggregate. And so you can change the chunk interval for the underlying hypertable when you create the hypertable. Here, the default chunk time interval is 7 weeks. But if you look up the timescale documentation, which is linked in the comments, thank you, whoever is doing that, thank you. You can set the optional parameter to set the chunk time interval. But you can, if you're referring to the time bucket size, you can also change that when you create the continuous aggregate. In this example, I have 1 day buckets. All right, I'm going to continue. Let's use the chat if you have more questions. All right, so where were we? Yeah, so we got the size of the continuous aggregate, which is around 4,500 kilobytes. Now let's see the origin. Let's see the size of the original hypertable that has the record level data. So if I run this query, we see that it's 1,500 megabytes. So it's obviously considerably larger because it has more data. It has the record level data. So you can already see the kind of difference that continuous aggregates make. So instead of 1,500 megabytes, the continuous aggregate is only 4,600 kilobytes, around that. Now you can also see this kind of information on a chunk level, which could be interesting if you are trying to compare like a specific time windows. Just like in this example, if I scroll up, we materialized only a specific time window, a window start and window end. So only that part of the data set is actually downsampled. And so let's look at the difference in size only for that time window in the dataset. So first we can see the original chunk sizes. So the chunk sizes of the underlying hypertable. As you can see, we have the chunks. We have the ranges for the chunks. As I said, by default, TimescaleDB sets a 7-day chunk time interval, and the original size on the right. So for example, 37 megabyte, 36 megabytes. So these are the original record level, the size of the record level chunks. Now let's compare this with the continuous with the downsample data set. So this is a more complex query, but basically what this will return, well, after I change the name of the underlying materialized table, what this will return is the difference between needed storage space you need for the uh, for the original data versus the downsample data. If I run this, uh, we see the name of the hypertable, which is demo intraday. In this case, the original size, as you saw previously, it's a little bit more than 100 megabytes. So that's the original hypertable size for the given time range, because we are only looking at the range that we downsampled. And so the downsampled size is a little bit more than 4,600 kilobytes, and as a result, that is more than 99% downsample ratio, if you can say that. So as you can see, we downsampled a lot in size, and in practice, what this means is that instead of having minute level data, now we have data per day. So instead of having data for every minute, we have data for every day, and obviously for every symbol in the database. But with this, we actually didn't do a very important part, which is dropping those underlying chunks that still has the raw the record level data. And again, it's an important step if you want to reduce the needed disk storage uh, space. So to show that we actually delete data, let's see what's in the row hypertable. So let me just run this query, which is which will show how many rows we have between December 21, 2020 and August 31, 2021. So we have less than 7 million rows in that range. And remember that is the range that we downsampled, meaning we created the continuous aggregate. And so now we are ready to just delete this range of data. And as I mentioned previously, we are using the drop chunks function with two parameters. One is the newer than, the other parameter is older than. And basically what this will do, it will drop chunks in that time period. And now, before I do this, this is important that important to know that it will completely remove data. So once you drop chunks, unless you have some backup, you won't be able to recover it, because it actually deletes data. So make sure to know what kind of time range you want to define, and what data you want to delete. But I'm using a demo database, so I will just delete these chunks, especially not just because of a demo database, but also because I already I created the continuous aggregate, so I still have the downsample data in the continuous aggregate. All right, so if I drop the chunks, as you can notice, so we deleted multiple millions of records, and it was actually quite fast. And again, the reason for this is because we're using drop chunks, so we are not deleting records row by row, because that would be slow. We're using the drop chunks function, which will drop chunks which has a lot of records in them. And so this way it's much quicker. So we deleted the actual underlying row data. Now let's see what's left in the row hypertable. And I'm querying that time range that we downsampled, and querying how many row in the next query, and querying how many records left in the underlying hypertable. Because actually, you might expect that all of the records have been removed, but because we have used the drop chunks function, there might be some records left. So if I run this, you see that instead of having multiple millions of records, we only have more than 200,000 rows. And the reason we still have rows is that a chunk, if you use the drop chunks function, a chunk will only get dropped if it only has data in the given time interval. So if a chunk has data from the given time interval, but it also has data from that is, let's say, older, then that chunk won't be deleted. So this is actually expected behavior, but it's still, we could remove the other rows using the delete SQL function if we want to, but it's already better than having 266,000 rows. Is already much better than storing the I think it was 6 or 7 million rows. So this is already much better. And we can also see a small sample of the data from the downsample data set. So in this query, I'm actually querying the downsample data set, aka the continuous aggregate, just some random time range to see if it returns any data. And this is interesting because we just deleted the underlying row table, but the aggregated values should still be reachable. So this is what we're trying to see now. And as you can see, we got some data back. And the important thing is that now this is not minute level data. So you don't have one row for each minute. You have 1 day per row. So each symbol you have 1 day, and that day has the aggregated data for the open price, close price, minimum price, maximum price, and volume, based on the definition that we use to create the continuous aggregate. So basically, this is what we see in the result in the result of the query, the aggregated, or we could say the downsampled rows. So since it doesn't delete the chunk data, it can still be re-manipulated. Well, I think technically yes, because you still have the data actually stored in the continuous aggregate. It's materialized. So technically, I think yes, even though depending on what you want to do, because continuous aggregates store. So continuous aggregates doesn't store the actual. Sorry, I'm looking that way. The chat is on my second monitor. But basically, the TimescaleDB continuous aggregate doesn't store the actual values. So it doesn't store the actual, in this case, numeric values. It stores partials. Again, there is a whole like technical discussion why that is, but it stores partials, and but you still can get the data directly from the continuous aggregate if you query, just like how I did here. Let me find it. So if you can just query the demo downsample, which has the downsample data, which is the continuous aggregate, so you can still get access to the data and do basically whatever you want to do with it. Yeah, I highly suggest looking in the documentation, and also, if you want to learn more about continuous aggregates, we have a lot of other continuous aggregates videos on the YouTube channel, and also free to ask questions in the TimescaleDB Slack community. If you're not a member yet, you can find it on slack.timescale.com. And we're happy to answer more questions, or if you get stuck or anything like that. All right, so basically that's how you manually downsample data. Now, quickly, let's just cover how you set up these automation policies, um, which automate this whole process. So, as I mentioned before in the slide, to automate this whole process, you will need to set up two policies after creating the continuous aggregate. First, you will need a continuous aggregate policy, which will actually do the aggregation. So it will automatically insert new data into your materialized continuous aggregate. And then the other policy that you need is a data retention policy, which will remove the data. And as I mentioned before, it's important to make sure that these two policies don't conflict with each other, meaning that the interval that you define for the data retention policy should not overlap with the continuous aggregate policy. So in this example, I'm creating a continuous aggregate policy which will run every day. And it will update data that is between the last month and the last day. So that's the time window that we are using for the continuous aggregate policy. And for the data retention policy, the only parameter that we define here is the drop after parameter, which defines the interval or defines the time that will be used to select the data to be deleted. So in this case, all the data that is older than 1 month will be deleted. And these two policies, these two specific examples should work properly because they don't overlap. So basically you have, in the case of the continuous aggregate policy, data that is between 1 month ago and 1 day ago will be aggregated. So we could say this policy will do the downsampling part. It will do the aggregation. And then after it's done, data that is older than 1 month in the row hyper table, that data will be deleted. And so this way you automatically have a continuous aggregate which has all the aggregate data, but you remove the older historical data that you don't need. Now, the other interesting part is that this continuous aggregate view is not only useful because you are downsampling data and you are storing less data, but also because it has a portion of your database materialized. So whenever you're making queries using the continuous aggregate, those queries should be faster because the values are materialized, they're coming from the disk, and so it could be useful for other use cases, not just for downsampling purposes. All right, so that's all I planned for today. As I said, if you want to continue your journey learning about TimescaleDB, the documentation is a very good place for that. Also, I recommend joining the TimescaleDB community on Slack if you haven't done that already. Slack.timescale.com. And again, I'm available in that Slack community, and you can Slack me. You can also ask questions in the general channel if you get stuck, or if you have more questions regarding downsampling or really anything TimescaleDB related. And you can also tweet us Timescale at TimescaleDB, or if you want to personally reach out to me on Twitter, Attila Toth, that is my handle. And very important, we are hiring. We are hiring for a lot of different roles. So if you're interested in joining Timescale and the team, go to timescale.com/careers. And I hope it was useful. I will probably do one of these streams next week, but the team will do another Twitch stream tomorrow as well. So look at our Twitch and YouTube channels to follow that as well. And that's all I plan for today. Thanks for watching. Thanks for the comments. And see you in the next one.